Hi everyone, welcome back to the channel. I thought today I'll continue the series on the tape out of RFIC or MMIC design. So we've made several videos on this already. I just want to quickly show you here what we've done so far. So we did device characterization, extracting metal and dielectric constants from the PDK and Cadence to HFSS code design, at least part of it. And then we also made a couple of videos on cross-coupled oscillators. So I wanted to continue on oscillator design. So in order to discuss voltage controlled oscillators or VCOs, we need to first talk about varactors. So that's what we'll do in this video. So we'll basically look at the different kind of MOS varactors that are available and maybe, options of how we can improve on them as well. So it'll be a quick video, but I thought it'll be nice to do that. And we'll also look at Cadence and see how to simulate and characterize the performance of a given varactor in Cadence. Okay, so let's first jump into the intuition and some theory behind it, and then we'll later look at Cadence. Okay, so what we're looking at today is MOS varactors or variable capacitors, right? So this is nothing but variable capacitors, right? And then you really need them when you want to do voltage controlled oscillators, which are very important for different reasons, which we'll get into it in the VCO video. But essentially, you need to make capacitors whose capacitance you can control, right? So the typical symbol for something like this is a capacitor with an arrow to indicate that it can be controlled by a voltage, right? So that's kind of what it looks like. Okay, so there are two big sort of uh, cat, two different types, I should say, of varactors. So the first one is inversion mode, and the second one is accumulation mode. So we'll talk about both of them. And we'll focus only on MOS varactors, not on PN junction based diode varactors, because MOS varactors are just more popular and better performance, at least in CMOS processes. Okay, so in today's video, I'll focus on NMOS based varactors, but of course it's very simple to kind of go from NMOS to PMOS, right? So we'll start from a simple NMOS design. What does it look like? Right, and then we'll see how these varactors actually work. So, typical NMOS device looks something like this. You have an N plus region, another N plus region, and then you have your gate oxide, and then the gate contact on top of it, right? So that's the metal contact. And then you also have a body contact, P plus, and of course the substrate is P substrate. Right, so if you don't know any of this, then you should certainly go and watch videos or read a book or something on CMOS design. I'm not going to go into all this now, but of course, if you know it, then this is basic, right? So this is our gate contact. Let's say this is the drain. I'll say this is the source, and this is the body. It's a 4-terminal device, of course. And what I'll do is I'm going to make a copy of this. Copy. Okay. So typically in a MOS varactor, right, this is just a general MOS varactor. The way it's made is that you connect the source, drain, and body together, and that gives you one terminal of the capacitor, and then the gate gives you the other terminal, right? Something like this. Okay, so that's your two-terminal capacitor. Um, so there are two modes of operation, of course. The first one is I guess not, of course, there are two modes of operation. We can characterize it as strong inversion where you have VGS is much greater than VTH. And this is your typical mode of operation for a MOSFET, right? So in this case, the capacitance Okay, so what actually happens, right? If I make VGS very large, then you have a channel that is created down here of electrons, right? And then of course you have, let's say, positive charges here, and that essentially forms your capacitance, right? So you have parallel plate capacitor between this region and this region. And since this channel basically forms right underneath the oxide, you can approximate very well this capacitance as just the oxide capacitance of this oxide layer, right? This oxide layer. So that's why in strong inversion, the actual capacitance is very close to or approximately equal to the oxide capacitance, Cox, right? And that depends on the width, length of that junction of the oxide layer of the gate, I guess. Okay. The next thing is that the N plus channel and N plus, which is the drain N plus and the source N plus, form a low resistance bottom plate for the capacitor, right? So it's essentially the channel kind of shorts out the drain and source to create a very nice large bottom plate, right? So there is no extra resistance basically between the drain and source, no parasitic resistances or very less, right? So that's called strong inversion. The next case is, so let's do it right here. You have exactly the same kind of circuit. Connect these two, connect this, and your capacitance is here. Right, so the next one is accumulation, next region of operation. So what is accumulation? So accumulation occurs when VGS is less than zero, much less than zero. Not much less than zero, but less than zero, I guess, right? And we'll see exactly where it is. So in this case also, so what's this case? So this case is when you have electrons that are bunched up on the top metal plate, and they push away the electrons in the channel in the substrate, and you're left with holes basically as the carriers, and that forms another plate, right? So again, you can see kind of in this case, you have a bottom plate and a top plate, and the oxide layer is essentially the only difference, the separation between these plates. So once again, you have capacitance that is approximately Cox, right? So that's kind of nice that in both cases you get about the same capacitance. But there is an issue here, which is that earlier, the majority carriers, these channel, this channel, the electrons in the channel were coming from the drain and the source, right? They were providing these electrons because of course the substrate, P substrate is depleted in electrons or doesn't have an excess of electrons. So these electrons that form the channel come from the drain and source. Whereas in this case, if you want holes to come in, they have to come all the way from the body, right? Which is out there. It's not right next, not next to it. And because you have this long kind of um, separation between where you're forming these holes, where your holes are going and where they're coming from, this leads to a parasitic resistance, series resistance. So essentially you end up with a quote unquote large series parasitic resistance, right? That may not be a good thing because that reduces the quality factor of your capacitor. Okay, so from this kind of discussion, at least it looks like accumulation mode is worse than inversion mode, right? But right now, actually both these modes exist at the same time, right? So if you look at, let's say if I plot capacitance as a function of VGS, see as a function of VGS, what does it look like, right? So when you have, let's say, when your VGS is very large, it's a straight line, sort of, which is equal to COX. When VGS is also very small, it's also a straight line, right? And that's kind of what we said, COX. But when you're in the middle, when VGS is close to zero, the top plate of the capacitor is not charged, right? So it doesn't have a bottom plate essentially. You don't have electrons or holes that are pulled in. And that's why the capacitance kind of drops, right? The entire region is depleted, and that's called the depletion region, or the depletion mode rather than the depletion region. So you'll see that the capacitance actually drops quite a bit and then maybe comes back a little bit to COX, right? So this is kind of what the transfer characteristics looks like from voltage to capacitance. So we can label these different regions. So this region is accumulation. This region is so I'll actually label it like this. So this is accumulation, right? So this region is probably depletion, you can call it, depletion mode. Here you have a weak inversion. I won't really get into what that is, but it's the transition you can think of between the depletion and strong inversion. And then finally here is where you have strong inversion. Yeah, of course, you can subdivide it further to say weak inversion, moderate inversion, and strong inversion, but essentially that's what it looks like. And this is actually kind of undesirable because if you have a very large swing, then you may be swinging in this region, right? And you don't want the capacitance to go back up when the voltage drops. Ideally, you would want a curve either that looks like this, right? That's monotonic, or that looks like this. So essentially what we want to do is we want to create a varactor that has either strong inversion or accumulation, right? And that leads us to the two different types of circuits that give you either an accumulation mode varactor or a depletion or an inversion mode varactor. Okay, so let's discuss those. First is, let's say, inversion mode, MOSCAP. So what are we trying to do? We want to eliminate, in this case, eliminate accumulation, right? So that you only have a monotonic curve. Okay, so how do you do that? Let's go back to this Drake diagram. And if you go back here and we look, I said accumulation happens when you have charge carriers that go from the body into the body contact into the channel area, right? So we want to make sure that doesn't happen. So how do you do that? You can connect again the drain and source together. That gives you one contact. The gate gives you the other contact. And if you want to make sure that there is no, basically the gate doesn't pull holes from here, you need to make sure the body is at the same voltage or higher voltage than the gate, right? Or lower voltage than the gate. So essentially, okay, let me explain that a little bit better. So in accumulation mode, what happens, right? If you go back here, you have a very low, so let's say I apply -1 volt here, right? So you're ending up with a bunch of electrons here, bunch of holes over here, right? And you want to avoid this. If you want to avoid this, what you need to do is you need to make sure that this voltage out here is lower than -1. So we'll connect this to minus VDD. The lowest possible voltage that you have on your chip, right? If you do that, then um, this kind of whole current cannot flow this way, right? So it cannot create that bottom plate. And that's basically the idea. So now if you look at the CV characteristics, VGS, C, you should see no accumulation and only inversion. And then we'll see this in Cadence, of course. So at the circuit level, what does it look like? With an NMOS device, it looks something like this. Use black. So you have drain and gate that are connected. They give you one terminal of your cap. Sorry, drain and source that are connected. And then the body connection goes to minus VDD. Right, and the PMOS version is very similar. You can essentially just flip everything. It's kind of an ugly device, sorry. Your PMOS. Now this connects to VDD. And the connections are like that, right? So this is an inversion mode NMOS device. And this is an inversion mode PMOS device. Okay, so that's pretty straightforward, and we'll look at Cadence and see that this is actually the case, right? And the next one, let's quickly talk about that, which is the accumulation mode. MOSCAP. Okay, so in this case, we want to eliminate inversion. Right? So in order to do that, let's again make a copy of our trusted NMOS. And we again connect the drain and source. It's one contact. This is our second contact, and the body is the third contact, right? Okay, so if you want to eliminate inversion, what do you need to do, right? So in inversion, you have, let's say, 1 volt applied to the gate, right? So you have positive charges here, and they pull electrons in from the drain and source, right? So if you want to avoid electrons being pulled from the drain and source, you need to make sure that the drain and source are a higher voltage, right? So essentially, this gets connected to VDD, and this becomes your second terminal, the body, right? So your capacitance is kind of here, basically. Okay, so if VDD is at a higher potential, then you can't get inversion because electrons cannot flow from the drain and source into the channel, right? So it kind of kills that. Obviously, one thing you need to be careful in both these cases when you're biasing, let's say, the body at a separate voltage than the drain source and gate, is you need to be careful about breakdown when you have large swings. Right? And we'll do that when we look at VCOs. Because you're biasing, let's say, at VDD, you may have a large swing, right? So swing and junction breakdown, basically. So that's something always to keep in mind when you do large signal analysis or large signal circuits. But I just want to mention that. Okay, what does the CV characteristic look like? It looks something like this. You have only accumulation, which is this one, and you don't have inversion, right? Okay, so let's quickly look at the circuit, what it actually looks like. So it's pretty simple. So this one goes to VDD, and then that's your accumulation mode in MOS. And you can do the same for PMOS as well. Of course, now you would connect to minus VDD, and you can think about the layout and see in the layout what minus VDD actually does for a PMOS device, right? And you'll use the body contact as part of the cap. So this is accumulation mode PMOS. Okay, so this still has the same problem of that parasitic cap, or parasitic resistance, right? Because your resistance out here, and then you have this small cap here, right? Basically, and that resistance can be large. In reality, actually, accumulation mode MOSCAPs are still used because they have actually better phase noise performance, and you can actually also get more bandwidth, faster sort of response. But you need to change the layout quite a bit for that. So how do you do that, right? So let's actually quickly address that. And that's actually how modern MOSCAPs are made, is that they use accumulation mode devices uh, that are slightly modified. Okay, so we want to improve accumulation mode MOSCAPs, right? So how do you actually improve them? So if you go back here and look at this more carefully, the main problem, of course, was that these guys are kind of useless, right? We don't actually use them. They're If you can just get rid of them, then we still have a capacitance between this and this guy, right? But of course, just getting rid of them is not enough. What we can do is get rid of these and then move this body contact close to the gate, right? So you have a layout that looks actually much simpler. It's essentially just your oxide layer and then body contacts around it. Direct body contact, right? P sub. That's it. And then you can connect, obviously, these together. So that gives you one contact. And then your other contact is here. Right, so this is like a modern accumulation mode MOS Varactor. They're very fast. They actually can give you a large um, change in your capacitance as a function of voltage. So what are the advantages? So you don't have that parasitic resistance now because, of course, you brought the body contact much closer, right? There is no weak inversion. It is pure accumulation because there is no source of charge carriers for inversion to take place. Because there is no weak inversion, you can actually get slightly larger swing out of it. And there are some other impacts from weak inversion which you avoid. Then you have a large supply of majority carriers nearby, right, from the P plus regions. Okay. And then you actually also don't have any unnecessary parasitics, right? Because earlier we were taking a MOS transistor and then trying to like play some tricks to get rid of either, the drain source or the bulk contact. And that always leaves some parasitics in, because you have something that you're not using, right? So in this case, you don't have that. You eliminated unnecessary contacts and unnecessary regions, so you have a better uh, parasitic model, basically, cleaner, right? So no unnecessary parasitics. That's actually a big advantage. The downside, of course, is that such a varactor doesn't always exist in a PDK. So there are actually, we'll see in the GPDK, there is no such varactor. So if you're using a PDK that doesn't have something like this, then you need to custom layout your own device, which of course you don't have a model for unless you do some physics simulations, but you have to like kind of do a custom layout and then fabricate it, test it, see if it's working, characterize it. So you may have to go through a couple of runs to do that, right? So it requires custom layout and characterization. If big if not available in the PDK, right? If it is available, that's great because typically that means that they have optimized already the layout to get a very nice linear and good performance out of your varactor. So you have a very nice CV characteristic basically. Okay, we can actually slightly improve this even further. What you can do is that one kind of minor issue with this is that in this case, the majority carriers are holes, right? Because that's what is supplied by these guys, right? Because remember that accumulation mode only happens when the voltage is less than zero, right? So, and holes are slower. So in fact, it's better to use a PMOS version of this. So what does that look like? So you have an N well, and this is your P substrate, N plus, sorry, P plus, no, N plus, yeah. N plus, N plus, and then your metal contact on top, right? And of course, these two N plus regions form the other contact, right? So now the majority carriers, of course, are electrons, which is great, right? They're around 3 times faster than holes. So you also get better RF performance. So this actually is probably the most widely used, as far as I know at least, MOS Varactor today. This kind of layout architecture, because it's very fast, you get a large CV characteristic, um, and the phase noise performance also is actually better. So anyways, so this is, yeah, the main one. Okay, so with that, we can kind of stop talking about the intuition and maybe some theory. I haven't really done any real theory, but mostly intuition, right? Based on the layouts. So what we'll do now is that unfortunately in the GPDK, we don't have a model like this. But as far as I know, there are several other PDKs that do offer MOS varactors. So you have to look at RF MOS varactors, and you'll see that they are usually PMOS varactors, although you have the option also of NMOS. Uh, but yeah, okay. So let's go into Cadence now, and we'll actually take a regular transistor, and then we will connect it up in different ways and see what the capacitance, what the Q, and what the CV characteristics looks like. Okay, so since I've already done a few circuits before, I'm not going to explain everything here. We'll just quickly go through and do our varactor design. Okay, so let's use a NMOS device and then connect it up. All right. Okay, need an inductor and we need a bias. right? So that's kind of like just a bias T basically to bias this capacitor. Uh, Let me actually just leave it here. So perfect. Actually delete this. Connect it up. Okay. So let's change this to VDC. I'll just make this 1 Henry. Sometimes this can give problems, so you should be careful with using very large values, but for a simple circuit like this, it's okay, I think. That's our first port. And then we can change some parameters here, maybe. And then this, right? Okay, so let's say I have 10 fingers, maybe 0 volts. Background. Okay, and then we need to do an SP analysis. Select this port and I'll do a design variable at 10 gigahertz. DC, go from minus 2.5 to 2.5 volts. Okay, and let's run it. All right, so results, direct plot, main form, Z parameters, real part. Actually, we need the imaginary part. Z11. Okay, and then from this we can calculate the capacitance, right? So the capacitance should be times the imaginary part is minus 1 over omega c. So this should be times 2 times pi times 10e9, because we are doing it at 10 gigahertz, right? So we can also plot that to verify it. That does not look right. Oh, it should be divided by. Okay. Delete that, delete that. Yeah, that looks right. Okay, so that's what we have. That's the capacitance. And you can see clearly that you have this kind of strong inversion on the right, and then maybe depletion, weak inversion somewhere in the middle. And then you also have the accumulation on the left, right? So how do we make sure that this is the right capacitance? I always like to test if my equations are correct, right? So there's a simple way to do that. So let's go back in here. We can delete this. Say this is capacitance. Hit OK. And the simple way to verify it is to just kind of replace this. And I'm using a lot of hotkeys, which I have on my website, the Cadence hotkeys. I'll leave a link in the description for you to take a look at that document in case you're using Cadence for the first time. But okay, so put a cap and a resistor. Forget the resistor. Let's just do a cap, right? And then let's run this. And it's 1 pico, right? So that's correct. And just to be even more careful, you can make this 3.4 pico. And then let's run it. Okay, so you know that the equation is correct, basically, which is obviously kind of trivial in this case, but it's good to check. Okay. Okay, so if you go back to our MOSCAP and run the simulation, we see that we have this kind of behavior, right? And we said that if you want to operate it in pure inversion mode, then what you need to do is we have another one bias circuit. And this needs to be connected to minus VDD, so minus 2.5. And that connects to the body, right? So this should get rid of the accumulation mode, and you end up with just inversion. So let's test it. There you go, right? So the accumulation mode kind of disappeared, and you only have your strong inversion and maybe even some weak inversion, right? So that's obviously one way to do things. Of course, things have shifted. It's not exactly going to be on par with this. But the other approach was to say, okay, can we get rid of inversion and just have accumulation mode, right? And that also is possible. And we said that the circuit to do that is one that looks like this. This connects straight here. And this one is VDD, so 2.5 volts. There you go, right? So you can kind of see that this plot is a lot more smooth, right? And you get a slightly larger swing as well, and good linear response out here. Right, so that's kind of the basics behind. So that kind of verifies that you can take a typical MOS transistor and get a nice CV relationship out of it by either eliminating accumulation or strong inversion, right? And we haven't really done custom layouts or anything because you can't really verify that here. But in this PDK, unfortunately, there isn't a layout that I can show you of a dedicated MOS Varactor that uses an accumulation mode PMOS device. But if you do have a PDK like that, then you can take a look at that and see that that's in fact the case, that what we discussed is that you can get rid of the drain source and you just have one body contact, and that gives you a really good performance. Okay, so that's pretty much all we need. We'll either use the accumulation mode or the inversion mode when we design circuits. Since we only have an option between these two, and you don't have the ideal accumulation mode device, I think it's better to go with the inversion mode. It's faster. The NMOS inversion mode is faster because it uses um, electrons as the majority carriers, and you don't have those parasitics, right? So even the Q is better. So if you don't have access to a dedicated MOS varactor, if you have to make it out of a transistor, my recommendation is to use strong inversion, especially for RF performance, and that's what we'll do. So we'll kind of rely on this one. Okay, so I don't want to make this too long. Hopefully it's a nice, interesting video. In the next one, we'll look at VCO design based on these varactors. And we'll do layouts, and also we'll look at how to do layout of inductors and things like that in Cadence using HFSS. So hopefully you're excited about that. And I'll see you in the next one. Thank you.